In this statistics lesson, we will be discussing measures of variation. Please feel free to pause and read through today's objectives. All right, our first objective is to find the range of a data set. To do that, you just take the maximum entry minus the minimum entry, and this is probably something you have done before. So, for example, 2 corporations each hired 10 graduates. The starting salary for each graduate are shown. Find the range of the starting salaries for both corporations. So if you'll notice for Corporation A, let's start there. Let's start with Corporation A. The largest salary was $57,000. And we're going to subtract the lowest salary, which was $47,000. So the Corporation A has a range of $10,000 in their salaries from the lowest to the highest for starting salaries. Now let's look at Corporation B. Its largest starting salary is $68,000 and its lowest is $33,000, which is a difference of $35,000. So what does that tell us about these two companies? All right, so this is where we start talking about variation. What is variation? So as you can see, both of the data sets have their means were the same. So if you did calculate their means, you would find that they have the same mean, they have the same median, and the same mode. But unfortunately, they're very different when it comes to their ranges. And this is because that second data set has what we call a greater variation. The data is much more spread out than the data from Corporation A. And this can lead to a lot of questions about the companies themselves. So let's look at some histograms of that data. So here are the histograms of the data. And as you can see, Corporation B is much more spread out than, notice Corporation A, the starting salaries are all clustered together, and in Corporation B, they are not. So this might affect you if you decide to take a position. They might tell you, hey, our mean salary is $51,500, and you're like, great. And you get hired on by Corporation B, and they start you at, $33,000, and you're like, wait, whoa, what the heck just happened? And if you start with Corporation B, they might start you at $47,000. Big difference. So knowing how varied those starting salaries are might also affect your decision to go work for either of these corporations. All right, so that is kind of what our basic discussion on variation is. Then there's another word called deviation. Deviation talks about how each data point varies from the mean. So if you're talking about a population set, the deviation would be X, your data point, minus the mu, the population mean. If it was a sample, same thing, X, your data point, minus the sample mean. So how far are you from the mean? That is what variance means, deviation means. So variance is just talking about the data as a whole, how spread out it is. Deviation talks about how far each data point is from the mean. Now we can calculate both of these measures, both deviation and variance. So here is the traditional formulas that you would use. So if you're talking about a population, the variance would just be the sum of all of those deviations and you want to square those deviations. So take the deviation for each point, add it, square them, and then add them all up, and then divide it by your total number of data points. And again, your standard deviation is just going to be the square root of that variance. So in order to calculate standard deviation, you really do have to calculate variation first. Variance often doesn't have a practical application in a lot of problems because everything is squared. So like if you're talking about, starting salaries, your variation would be in dollars squared, which doesn't really make sense contextually. So a lot of people talk more about standard deviation, mostly because we have a lot of applications for standard deviation in future work. But just so you know that standard deviation does come from the variance. All right, so the standard deviation measures the variation in the data set about the mean and has the same units as the data set. So if your data set's in money, the standard deviation will be in money. The standard deviation is always greater than or equal to 0, and the only time the standard deviation will be equal to 0 is if the data set has no variation, meaning every single data point is exactly the same entry. And as your entries get farther and farther away from the mean, that means that your standard deviation will increase, right? So if your data is really, really spread out, then you're going to have a higher standard deviation than if your data was clustered together, like when we talked about those starting salaries. So if you were going to find your variance and your standard deviation for your population, you would have to go through this process. So the first thing you'd have to do is find the mean of the data set. Then you would have to find the deviation of each entry, and you would have to square that deviation. Once you've done that, you would add all of those sum of squares up, and you will often see that SS sub x. That's what that means, sum of squares of all your x's, all your data points. And then you would divide that by the number of data points in your population, and that would be your variance, and then you would just take the square root of that to get the standard deviation. All right, so in this example, I've given you that starting salary data set for one of those. That's the corporation A, and I would like you to find the population variance and the standard deviation of those starting salaries. I've made this little chart to help you get your work organized, and it will take you a while. A lot of this work is very tedious if you do it by hand, which is why people usually use technology to find those things. So I'll just get you started on it, and then I will show you the completed chart. So the first thing you need to know is that there are 10 starting salaries, so that's n equals 10. If I add up all my x's, if I sum those x's, I get 515. So calculating my mu is just going to be 515 over 10, which gives me that 51.5. All right, and then you will need to find the deviation for each data point. So you're going to take 51 and subtract 51.5, which would give you 0.5, and that would be negative. Of course, the negative won't matter because you're going to square that, and then that would give you positive 0.25. And then you would repeat this process for each data point. 48 is below, so that would also be negative. That's going to be negative 5.5. No, 3.5. I can't do math. See, this is what happens when I don't use a calculator. So negative 3.5, and then you would square that, which would be positive 12.25. And then you would just repeat this for the entire list. When you are done, you would need to make sure that you sum each column. And so let me show you what the completed, if you want to do this on your own, please feel free to do that. Let me show you the completed chart. So here's the completed chart. Notice that when you add up all your deviations, they should add up to 0. And then notice our sum of squares. The sum of all of our squares of our deviations add up to 88.5. And those are the two things we need to calculate our variation. So notice when we do our variance, that is just the sum of the squares. So this one right here, which is 88.5. And we divide that by our 10 data points, and that gives us a variation of $8.9 squared, which doesn't make any sense. So standard deviation would just be the square root of that, so the square root of 88.5 over 10, and that is approximately 3.0. So that means $3,000. So that means that every $3,000 away from the mean is a standard deviation. And we will talk a lot about how we can use that information to discuss position of data, and that's what we're going to do in the next lesson. So it all kinds of ties very nicely together. Now, using populations is something we don't do very often. So more often than not, you're going to use a sample. So sample variance and standard deviation are the same, right? You use exactly, instead of mu, it'd just be x bar, but notice instead of n, it's n minus 1. And that's because we do have a sample, and we do have to adjust a little bit because we have a sample and we don't have a population. Those, as you can see, can be kind of tedious and time consuming. So there are actually 2 shortcut formulas that you can use that I highly recommend. Because notice all you have to do to use these shortcut formulas is know your n. You have to know the sum of your x squareds, which is very easy to do. Like take the x squared and then add them all up. And then your sum of your x's, which you've already found when you found the mean. So I like these shortcut formulas a lot better just because they're a lot more efficient than using the sample variance. And if you have a calculator of any kind, if it's already programmed in there, like in Excel it's already programmed in there, they will use those shortcut formulas because they are more efficient as far as computing time as well. So the steps are exactly the same as they were before for finding variation and standard deviation for a sample, except you're dividing by n minus 1 instead of by n. But the steps are identical. But again, I would use the shortcut steps because all I have to do is find the sum of the x's, which I already found to find the mean, find the sum of the x squareds, and then plug them into the shortcut formula for variance, and then take the square root of that, and that will give you the standard deviation. So I just find that to be a lot fewer steps and much more efficient than the other way around. All right, so if we look at Corporation A and think of it as a sample instead of a population, which it usually is, go through the process and find these. All right, so the first thing I note is that n is 10. I know that the sum of my x's is 515. I calculated that in my last one. So my standard deviation, my mean of my samples is going to be 515 over 10, which is 51.5. Again, no difference than your population mean. And then if you want to find the standard deviation and the variance using those shortcut formulas, we already have the sum of the x's and we have the n, so all we have left to find is the sum of the x squareds. So I would just take 51 squared plus 48 squared plus 49 squared, again, in my calculator. And when you add all those up, you should get 26,611. So I now have everything I need for my shortcut formula. All right, so just to refresh your memory for variance, here is my shortcut formula. N times the sum of the x squareds minus the sum of the x's, and then square it, and all that is divided by n times n minus 1. All right, so all you have to do is plug it in and then use your calculator to simplify. So 10 is my n, my sum of my x squareds is 26,611, minus the sum of my x's, which was 515 squared, and then divide that by 10 times 10 minus 1, which is 9. So again, make sure that you're really comfortable using your calculator. So that turns out to be 885 over 90, which is approximately 9.8. So your variance for the sample is $9.8 thousand squared, which again doesn't make any sense. And then if you want to take the square root of that, that will give you your standard deviation. So the square root of 885 over 90. And that will give you approximately 3.1. So $3.1 thousand is your standard deviation. So I find that to be a much more efficient method using those shortcut formulas. So I highly recommend that you do the same. All right, so here is another example. Same thing. If you would like to press pause and try these, try to find the sample variation and the standard deviation of the recovery times for these high school football players in this given data set. So please feel free to press pause and then we'll walk through it. All right, welcome back. All right, so there are 12 high school students that we talked about here. The sum of the x's was 90. This means the mean, oh, and this is a sample, is it not? Yes, it is a sample. So I'm not going to use mu, I'm going to use x bar because it's a sample. So my x bar turns out to be 90 over 12, which is 7.5. So the mean recovery time is 7.5 days. Make sure, and again, make sure you have a label on there because that helps. All right, and then if I want to use the shortcut formula to help me find that sample variance and that sample deviation, the only other thing I need to know is the sum of the x squareds. So I would just take 8 squared plus 10 squared plus 4 squared, add them all up, and I should get 726. And then I would just put that into my variance formula. So n is 12, sum of my x squareds is 726, minus the sum of my x's, which was 90 squared, and then all of that divided by 12 times 11. So my numerator turns out to be 612, and my denominator turns out to be 132. So divide those, and you get about 4.6. So the variance is 4.6 days squared, which again doesn't make any sense if you put the label on there. So standard deviation is just going to be the square root of 612 over 132. So I put that in my calculator, and I get about 2.2 days. So notice, very simple if you're going to walk through and use those shortcut. If you were going to use the traditional, it would be much longer. So let me walk you through that. So you'd have to make your little chart with your times here, and then your deviations, and then the sum of those deviations. So that would give you your SSX of 51. And then you would have to put that 51 here divided by 11, and you get 4.6, and then take the square root of that 51 over 11 and get 2.2. So notice we got exactly the same answers. So just to show you that the shortcut formulas really do work, we're not just making them up. So just know that that is a much more efficient way to use those shortcuts than to create that chart and walk through all the steps. Using technology is also great, especially if you have a larger, like if this was the data set I gave you. Obviously to do this by hand would take a little bit of time. So this is where we highly recommend that you use technology. And again, there are many many different things that you could use. You could use Minitab, you could use Excel, you could use a TI-84 calculator, you could use StatCrunch if you're using the Pearson products. There's lots of things that you can do that. But notice, no matter which technology I'm choosing, the mean is the same in all of them, and the standard deviation, which I have circled in all of them, is also exactly the same. So it doesn't matter what technology you use, you should get exactly the same answer. So please feel free to use technology if you have a bigger set, but if you have a smaller data set, then you can do them by hand without too much of a problem. All right, so let's talk about interpreting standard deviation. What is it? So standard deviation is just the measure that a typical data entry will deviate from the mean. So typically. So I have 3 different graphs here, histograms to show you. Notice the first histogram on the left is all the same entry over and over and over again, right? It's just 5, 5, 5, 5, 5, 8 times, right? 8 times we have the number 5. So the mean is obviously going to be 5, and the standard deviation will be 0 because there is no deviation from that mean, right? Every data point is 5 and the mean is 5. So there's no deviation at all. So no standard deviation. Notice in the one in the middle, we've got a little bit of spread, but the vast majority of our the mode and the mean and the median are all the same. They're all 5. This one, because they're a little bit more spread out, has a standard deviation of 1.2, which means your typical entry is 1.2 deviations from the mean. So if 5 is your mean, then it would be about over here would be standard deviation, and over here would be a standard deviation. We went to the right and to the left. So notice that that is where the bulk of our data is. And then the last one shows a gap, right? We still have 8 data points. We still have a mean of 5, but because they're so spread out, we've got data down here and then we've got data up here, that the standard deviation is much larger. It's a standard deviation of 3. So you can start thinking about how these standard deviations look. And then what it means for the data when you actually see the data in a histogram. Again, another great thing about those histograms and those graphs. All right, so I'd like you to try the same thing. Here are 3 different graphs, 1, 2, and 3. They all have a population of 8, and they all have a mean of 4. And what I'd like you to do is try to estimate that standard deviation based on what you see given that last example. So press pause, give it a try. All right, welcome back. Let's look at number 1. Number 1 should have a standard deviation of 0 because there is no deviation from the mean, right? The mean is 4 and all the data entries are 4. So that should have a standard deviation of 0. Now let's look at the second one. The second one is a little, notice that we have no data points of 4. Our data are only 3 and 5. So this should have a standard deviation of 1 because all of our data is either 1 above 4 or 1 below 4. So that would have a standard deviation of 1. And then if we look at the last one, we have data that is, here's our mean is 4. We've got data that's 1 away and data that's 3 away. So the population standard deviation would be about 2. Turns out it's actually 2.2. But if you said 2, I would totally count that right. All right, so when we interpret our standard deviation, there's this great rule that's called the empirical rule. And we will talk about this several times throughout statistics. It comes up over and over again. This is for any data that has a symmetric bell-shaped distribution. So you're looking for the peak in the middle and then going small on the ends. If your data is indeed bell-shaped, this nice symmetric bell shape, then 68% of your data will lie within 1 standard deviation of the mean. 95% of your data will lie within 2 standard deviations, and about 99.7% of the data will be within 3 standard deviations of the mean. And for those of you who are visual learners, here is a visual representation of that. So notice our mean is in the middle, 1 standard deviation to the left or the right, that would be 68% of our data. Notice it's about 34 on each side. And then if we went 1 more standard deviation, 2 standard deviations, that would be 95%. So from here to here would be 95% of my data would be in here. And then if you went 3 standard deviations, it would be 99.7. And we can use this empirical rule to help us solve problems. So a couple other things that you might want to know is that notice with the mean, if you add these up, we should have 50% of the data over here, and we should have 50% of my data over here. So that also, that mean splits our data in half, which is also another good thing to remember. All right, in a survey conducted by the National Center for Health Statistics, the sample height of women in the United States, aged 20 to 29, was 64.1 inches, with a sample standard deviation of 2.6 inches. Estimate the percent of women whose heights are between 58.9 and 64 inches. So 64 inches we know is the mean, right? So I'm a big fan of, having graphics because I like learning visually. So here's my mean, which is 64.1, right? And it wants to know the percent of women whose heights are between 58.9, which I know is below that. So let's go 1 standard deviation below the mean and see where we end up. So here's my mean, and then I'm going to subtract 1 standard deviation. So if I do that, I should better get my calculator up because I don't want to mess this up. So feel free to use your calculators as much as you want. All right, so we're going to take 64.1 and we're going to subtract 2.6. And that's going to put me at 61.5. Not quite where I want to be, right? I want to be at 59. So let's do another one. Let's take the mean and subtract 2 standard deviations. So let's subtract another 2.6. And I get 58.9. So, all right, so they want to know what is the percentage of people in that shaded area. All right, so if you go back to the chart that we had before, we knew that this block right here, that first block, is 34%. And then this next block is about 13.5%. And again, if you use technology, you can get better and better, but we're just going to kind of estimate this one. All right, so if I add those two, remember these are symmetrical, so if I add those two together, 34 plus 13.5, notice I get, let's see, that would be 47.5. So that's about 47.5. Now here's the cool thing. If you use technology, you can get a little bit better representation of that percentage. But for now, I'd be totally happy with that. But if you use technology, it turns out it's 47.72%. But notice we're pretty close, right? 47.5 versus 47.72. So don't be alarmed if you're a little bit off when you use technology, because we're just rounding. But again, I'm just looking for ballpark answers here. I'm not looking for perfection. I'm looking more for you being able to understand the material than I am about the actual numbers that you're getting at the end of the day. All right, IQ is often used when talking about the empirical rule, because IQ scores do have a symmetrical bell-shaped distribution. The mean IQ is 100 and the standard deviation is 15 points on that IQ scale. So what percent of IQ scores are between 70 and 130? So again, I'm a fan of drawing the picture. So here's my picture, right? I am at my average, my mean is 100, so that's going to go in the middle. If I go one standard deviation in each direction, right? If I go an S here and an S here, add 15 would be 115, and if I subtract 15, I get 85. So I'm not quite there yet. I want 70 and 130. So let's go another standard deviation. So we're going 2 standard deviations now. So 115 plus another 15 is 130. Perfect. And 85 minus another 15 would give me 70. So there's my spread, right? I am 2 standard deviations. So this is the mean plus or minus 2 standard deviations in each direction. So if I am 2 standard deviations away from the mean, that means that I have 95% of my data using that empirical rule. And then you could break this down also as well. Like if I only asked you from 100 to 130, right? What if I only asked you from 100 to 130? Well, it would just be this area right here. It would just be half of that, right? Because here's the other half over here. So 95 divided by 2 would give me, again, and I'm not doing this in my head because I don't want to mess up, 47.5%. So I could make 20 different questions just based on this one little drawing, which is kind of nice. So you can use that, that empirical rule in many different ways to help you. All right, what do you do if you don't have a bell-shaped distribution that's symmetric and pretty? Okay, then you can't use the empirical rule. What you're going to use is something called Chebyshev's theorem. And Chebyshev's theorem just says, and it's a very rough estimate, by the way, so please don't think that this is going to give you any really good, it's just a very rough estimate, that the portion of the data lying within k standard deviations of the mean is at least 1 over 1 minus k squared. So if I wanted to find the portion of my data that's 2 standard deviations away, so that's going to be k equals 2, I'm going to put 2 into that formula, and I get 3/4. So that means that about 75, at least 75% of the data, and again, that's the important part, that at least 75% is going to be within 2 standard deviations. And if your data happens to be a pretty bell-shaped distribution, that's going to be 95, right? And 95 is much higher than 75, which is fine. It's at least 75. So Chebyshev's does fit in this situation. And if you wanted 3 standard deviations, you would put in k equals 3 into the formula, and you would get 8/9, and that is 88.9%. At least 88.9% of your data will be within 3 standard deviations. And again, this is for any distribution. So let's look at some examples. So here we have the US Census data on age of people in Georgia versus age of people in Iowa. And obviously these are not pretty and bell-shaped, so we can't use our empirical rule, but we can use Chebyshev's theorem for the data, and they want to do 2 standard deviations, k equals 2. What can you conclude? And then they ask you a second question: is the age of 90 unusual for a Georgia resident? So let's talk about those 2 things separately. Okay, so let's look at k equals 2. Let's see. So, and we're doing for Georgia only. All right. So Iowa, I don't even need to think about. So let's just look at Georgia for now. Okay, so we're going to do k equals 2, which means we're going to take our mean and do 2 standard deviations. So 38.2, and we're going to do, let's see, plus or minus So let's start with the minus first. Let's start with the minus two standard deviations. And when I do that, that gives me -7. Now, I can't have an age of -7 years old. So going 2 standard deviations below the mean doesn't really tell me anything because I can't be -7 years old. So let's go above and see what happens. Let's do the 38.2 plus 2 standard deviations, and that gives me 22.6, which is 83.4. So that tells me that between the ages of 0 and 83.4, I have at least 75% of my population for Georgia. Okay, so that's between 0 and 83.4. That is 75%, at least, right? At least 75, and I should put that, at least 75% of my data is going to be there. And then the second question says, is the age of 90 unusual for a Georgia resident? And usually when you're talking about statistics, if anything is more than 2 standard deviations away from the mean, it's considered unusual. And we will talk about more specifically what that means later on. But for now, obviously 90 is much higher than 83.4, so we could say that the age of 90 is unusual for the state of Georgia. And we might find different results if we look at Iowa. So again, something that you should think about, and you can compare and contrast. This is another nice thing about having, the more we know, the more we can compare and contrast our data sets. All right, now what if they just gave you this histogram and they didn't give you any data? They didn't give you that mean and that standard deviation. What would you do? All right, so the first thing you'd have to do is you'd have to go look at the frequency distribution that goes with that histogram. So you may have to create that. And then you would go through and to find your standard deviation, you would just take you find your sum of your squares, right? You'd find the sum of your squares. But because we don't have x's, you may need to use the midpoints for each class. So if you don't have the x's, if you don't have the actual data, just use the midpoint for that particular class as your x. And then you'd have to find all the mean. You'd have to find the mean first and do all that. And again, I find that to be very tedious. So I'm going to usually use the shortcut formula, which is very similar to our shortcut formula before. So this time we're going to take the square root of n times the sum of, you take the frequencies times those midpoints squared, add those up, multiply by n, and then subtract the sum of the frequencies times the midpoints, sum those up, and then square them. That's your numerator, and then divide by n times n minus 1. And again, I'm a much bigger fan of the shortcut because I find it a lot more efficient. So say you were given this problem right here, but I gave you the data just so you could see it, but let's say I didn't have that data. All I had was this frequency distribution chart over here on the left. All right, so find the sample mean and the sampled standard deviation of the data set. All right, so first thing I want to add up all my frequencies, and my frequencies add up to 50. So there are 50 households that they asked, and they asked them the number of children, and there were 0 through 6. So let's first of all find the mean of my sample. So that you need, first of all, you need to multiply your f times your x's to find your mean. So we have to multiply all these. So that's 0, that's 19, that's 14, that's 21, that's 8, that's 6, that's 24. Add all those up together and you get 91. So my mean would be 91 over 50, which is approximately 1.8. So just under 2 kids per household, which seems fairly normal. All right, but if you want to find the standard deviation, you have to find the frequency times the x squareds. So that would be 0, right? 0 squared times 10 is 0. 1 squared times 19 is 19. 2 squared is 4. 4 times 7 is 28. 9 times 7 is 63. 4 squared is 16. 16 times 2 is 32. 5 squared is 25 times 1 is 25. And 6 squared is 36. And 36 times 4 is 144. I would add all those together. I would get 311. All right, so I would go to my formula. Right, so here is the standard deviation formula. You take your n, which is 50, and you multiply that by this number, the sum of the fx squareds, which is 311, and then you're going to subtract the sum of the fx's squared, and then you're going to divide that by 50 times 49. So when you simplify your numerator, you should get 7,269, and when you simplify your denominator, you should get 2,450. So take the square root of that, and you should get about 1.7 children. So your standard deviation is about 2 kids, one standard deviation. So the average was about 2 kids, and the standard deviation is about 2 kids. So again, this is, I think that shortcut formula takes up a lot less space. If you were going to do it the long way, here's the chart you would have to make to find those sum of the squares. And honestly, I am not patient enough. Notice when you plug it in the formula, you do actually get the same answer of 1.7. I just find that that shortcut is much, much faster to use. So I highly recommend that you do that. Sometimes if you are given pie graphs, you will definitely need to use a distribution as well, and you will have to use the midpoints because these classes for the sale prices of homes are set up from 0 to 90, 0 to 99, 100 to 199, 200 to 299. So you would have to find the midpoint for each before you could even get started. So this one would be 48.5. This one would be 148.5. This would be 248.5. This would be 348.5. This would be 448.5. And then about the plus, the 500 plus, that's where some debate might come into play. And for the sake of argument, we're just going to say it's 599.5. Again, but you can justify however you want to what number you're going to put there. All right, and then you would have to fill out this chart. And then once you've done that, then you would have to plug it into your formulas. Again, this would take a very long time. So I try to avoid problems like this on assessments, especially because that will take a very long time. But let me just show you how it breaks down. So there is my x's. I would find the frequencies of each, which were actually listed in the chart. Notice they were right underneath, 173, 129. So those were already there for us. Put those in the chart. And then find my f times x's, and then find my x squared times f's. I would add all those up and then plug them into my formulas. This can be very time consuming, which is why a lot of people really like to use technology to do this. But again, I want to focus on the nuts and bolts in this class, so be prepared to do this by hand. I will not give you a large data set when I give my assessments. Some of your professors might. I can't make any promises for them. All I can make promises are for my students. So please note that I would do a very small data set, something that would be very easy to do, like we have done in previous examples that we could do quickly. All right, again, you could still use the original formula if you wanted to. You would have to fill out this chart and then plug it in and find your, of course you'd have to do this chart first to find the mean, and then you'd have to do this chart to find the standard deviation. Again, I'm lazy. I want one chart that can take care of everything. So I would use the shortcuts if I were you. And the last thing we can talk about is how do we apply variation? If you ever take a business class, you will probably hear about the coefficient of variation when you're talking about comparing investment opportunities. So we will talk about that as our last example today. But first, let's talk about what it is. All the coefficient of variation is, it's just describing the ratio of your standard deviation to your mean. And your standard deviation is going to mean something, and your mean is going to mean something. And looking at the ratio of those things kind of tells you the higher that number becomes, the greater the dispersion level around the mean. So it's going to be dispersed out. So if you have a higher CV, it's going to be very dispersed and spread out. The lower your CV, the smaller, the more grouped that data is going to be. So let me give you an example. So if we have the heights and the weights of the members of the basketball team, and I would like you to find the CV for the heights and the weights. Now, to save time, rather than you having to go through and calculate everything, I'm going to tell you the mean. So let's start with the heights. So for the heights, the mean turned out to be 78.2, and you could easily find that just by adding them up and dividing by the number of players. And the standard deviation turns out to be 3.3, about 3.3. Sorry about my dog barking in the background. All right, so if I wanted to find my CV for the heights, so my coefficient of variation is just going to be 3.3 divided by 72.8, and I'm going to multiply it by 100 so I get a nice pretty percentage. And that turns out to be about 4.5%. So my heights are dispersed 4.5%, which it's a very small percentage, so that would tell me the heights are all pretty much the same, which if you think about it for a basketball team, that makes sense. You want a lot of tall players. So that makes perfect sense. Now let's look at their weights. Okay, same thing, I'd have to find the mean for their weights, and that turns out to be 187.8, and the standard deviation of their weights turns out to be about 17.7 pounds. So if you want to find the CV for their weights, that would be 17.7 divided by 187.8, multiply it by 100 to get that percentage, and that gives you about 9.4. Notice more spread out than their heights were, which also makes sense because people who are tall could have a heavier build, a more muscular build, a more slight build, especially in basketball. Depending on what position you play, you might be built differently. So it makes sense that their weights would be a bit more dispersed than their heights. So that's just an example of how you can use these CVs. But the place that I've seen it the most is in business classes. So say that you are going to talk to your financial guy, and he says, hey, I have these 3 opportunities for you to invest. I've got option number 1, which has a 5.47% average return annually, and its standard deviation is 14.68%, so on these stock prices. So that means it's got a pretty decent return. It's not the greatest, but it's decent. And we've got a low standard deviation. So that means that the prices of the stock isn't too spread out as far as the changing goes. So let's find the CV of that. So you're going to just take that standard deviation and you're going to divide it by your mean, which is 5.47. And then multiply it by 100, and that's going to give you 200.68. 2.68. So that is a pretty decent, and you don't even need to do the multiply by 100 in this case, because that doesn't, for our intensive purposes, we don't really need to worry about the percentage this time. So 2.68 is our CV. Do the same thing for each of the other options. Second option has a 6.88% return and a standard deviation of 21.31%. So 21.31, divide that by the 6.88, and you get about 3.10, give or take a little bit. And then your last option, which has the highest return, but has a pretty high standard deviation, and that would give you about 2.72. So when you compare these, the higher that CV gets, the more risky the investment is. And that's why you will find where you have these great returns, you're also going to have a lot of risk. So the mean is representing the return on your investment, and the standard deviation is representing your risk, how volatile that stock is. So it all depends, your answer will all depend on where you are in your financial investing. So if you're a young investor and you've got plenty of time to make up for any volatility in the stock market, you might go with that highest CV, right? You might go with this guy right here, because that's going to give you the greatest return on your money compared to the risk. Notice that's greater than over here. So we've got much riskier, but a decent return. Or you might go with this one, be like, I don't feel comfortable with that 21% standard deviation. Let me go with the lower one. And notice it's got a greater return. So this would probably be the most risky over here. risky, but great rewards. Best reward over here. This one is less risky. Whoops, I can't even spell. Less risky. There we go. But it's got a slightly smaller return. But they're both very risky. So say I was approaching retirement age. I probably wouldn't go with either of these options because I don't want the risk. I want something solid. So I'm going to go with this guy. It's got a lower return, but there's less risk. And if I'm approaching my retirement years, I don't have the time to account for the volatility in the stock market. So I'm going to go with the smaller risk with the lower return, knowing that I'm going to actually get more money. I'm going to get money back, but I'm not going to have that risk of losing money. So again, this helps just, especially with your investments, for you to decide which investment opportunity is the best for you based on the risk and return. So hopefully this has given you a nice overview of variance, standard deviation, and the spread and dispersal of data. And in the next lesson, we are going to talk about position of data. So like where the data points are compared to the mean and how does that affect things. So make sure you come back for that lesson as well. See you next time.